this is another lecture of affine geometry. The set V1, V2, Vn is linearly independent if per constant C1, C2, and so on Cn not all zero, such that the linear combination from 1 to n Ck Vk is equal to 0 if and only if Cj is equal to 0 for all j1 to up to n. If we write a vectors in the form of linear combination equal to 0, in which coefficient of each vector becomes 0, then such a combination is called linear and such a vector is called linear independent. While the set is called affinely linear independent if they are linear independent and also the sum of the coefficient from 1 to n Ck is equal to 1. Because for affine combination we need that the sum of the coefficient is equal to 1, then such a combination is called affine linear independent. Similarly, vector v1, v2, vn are linearly dependent vector if there exists lambda 1, lambda 2, lambda n not all 0 with linear combination lambda 1 v1 plus lambda 2 v2 plus lambda n vn is equal to 0. Vector v1, v2, vn are a finely dependent vector if there exists scalar lambda 1, lambda 2 up to lambda n not all 0 with linear combination s and the sum of the scalar becomes 0. If the sum of the scalar becomes 0 and linear combination is equal to 0, such a linear combination is called affinely dependent vectors. In R1, any two distinct vectors are linearly dependent but affinely independent. In real line, for example, we take two distinct vectors in R1 one-dimensional space. Then the two vectors are linear dependent but affinely independent. It means that the concept of linear dependent and affinely independent is different. Given here is a lemma. Given in affine subspace E vector plus let ai belong to I be a family of points in E. If the family ai bold ai ajj belong to I minus I set is linear independent for any I belong to I, for some I belong, then ai aj belong to I minus I. Assume that the family Aij belong to I minus I is linear independent for some specific I belong to I. Let k belong to I with k is not equal to I and assume that there are some scalar lambda jj belong to I minus k such that the summation lambda j ai aj is equal to 0 because the vectors are linear independent. Since ak aj can be written as ak ai inserting ai between ak and aj, ai aj we get summation lambda j ak aj is equal to j belong to I minus k lambda j ak ai inserting ai here and splitting the vectors j belong to I minus k lambda j ai aj. Now this lambda j ak ai plus j belong to I minus k lambda j ai aj which reverting this vector we get lambda j ai aj its own space minus j belong to I minus k lambda j ai ak. Here I inserted this summation I put here and I inverted this summation ak ai ai ak. Now and lambda j ai aj minus j belong to I minus k ai ak is equal to 0. This summation become 0 since the family ai aj is linearly independent. Because for linear independent we put the summation equal to 0, we must have lambda j is equal to 0. In this summation is equal to 0, no, we have for linear independent vector lambda j is equal to 0. For all j belong to I minus I k, this summation in this summation lambda j must be 0 and lambda j is equal to 0, j belong to I minus k means lambda j is equal to 0 for all j belong to I minus k. Given in a fine space such that ai be a family of points in E, the family ai belong to I is finely dependent if and only if there is a family lambda I such that lambda j is not equal to 0 for some j belong to I. Summation lambda I is equal to 0 and summation lambda I x ai is equal to 0 for every x belong to the affine space. The family AI belong to I is affinely dependent. If and only if the family of vector AI belong to I minus I is linear independent. For some I belong to I. For any I belong to I, the family AI belong to I minus I is linear independent. If and only if there is a family lambda J belong to I minus I such that uh, such that lambda j is not equal to 0 for some j, and such that j belong to I minus I lambda j aj is equal to 0. Then for in x belong to E, we have j belong to I minus I lambda j aj is equal to lambda j belong to I minus I lambda j. Here we can write as xij minus xaj. If we revert, then we can write as j belong to I minus I lambda j x aj minus j belong to I minus I lambda j x ai. Here let lambda I is equal to this summation. We get belong to I lambda I x ai is equal to 0, with lambda I is equal to 0 and lambda j is not equal to 0 for some j belong to I. Conversely, let set x is equal to ai for some I such that lambda I is not equal to 0. Since summation lambda I is equal to 0 implies that lambda j is not equal to 0 for some j is not equal to I. A family of two points A, B in affine space E is affinely independent if and only if AB is not equal to 0. If and only if A is not equal to B. If A is not equal to B, the affine subspace generated by A and B is the set of all points 1 minus lambda A plus lambda B, which is the unique line passing through A and B in same line of family of 3 points A, B, C, and E is affine. Similarly, 3 points A, B, C, and E is affinely independent if and only A, B, and AC are linear independent. Implies that A, B, C are not on the same line, not collinear. Not collinear. Here, a fine subspace generated by ABC is the set of all points 1 minus lambda minus mu A lambda B plus mu C, which is unique plane containing A, B, and C. A family of 4 points A, B, C, D, and E is finally independent if and only if A, B, A, C, A, D are linear independent, which means that A, B, C, and D are not in the same plane. Remark: given n plus 1 affinely independent points a0 a1 up to an in E, we can consider the set of points lambda naught a naught lambda 1 a1 lambda n a n, where lambda naught lambda 1 lambda n is equal to 1 and lambda I greater or equal to 0 lambda I belong to R. Such affine combination are called convex combination. This set is called convex hull of a0 a1 an points. If n is equal in this combination, if n is equal to 1, we get the segment a0 and a1 including a0 and a1 as. If we take n is equal to 2, we get the interior of triangle whose vertices are a0 a1 a2 including boundary points such as this is a0 a1 a2, which make a triangle in plane. Similarly, if n is equal to 3, we get the interior of tetrahedron whose vertices are a0, a0, a1, a2, a3, including their boundaries. These are the boundaries of faces of tetrahedrons. Similarly, a0 plus lambda 1, a0, a1, lambda n, a0, a1, such that where lambda I plus 0 to 1, lambda I belong to R, is called the parallelotope spanned by a0, a1, an, where en has dimension 2. A parallelotope is called parallelogram if dimension of affine space is 3, then parallelotope is called parallelopiped. Convex set. A subset V of E is convex if for any 2 points A, B belong to V, we have C belong to V. For every point C is equal to 1 minus lambda A plus lambda B, with lambda belong to 0, 1 close interval. Any point X in the plane ABC can be expressed as X is equal to lambda naught X plus lambda 1B plus lambda 2C, where lambda 1 naught lambda 1 lambda 2 is equal to 1. How to compute lambda naught lambda 1 lambda 2? Let A, B, C be 3 points and X be the any points be the coordinates of A, B, C, X respectively in the standard form of A3. To solve the system of equation A0, A1, A1 B1 C1 A2 B2 C2 A3 B3 C3 lambda naught lambda 1 lambda 2 x1 x2 x3. We will solve this system for x1 x2 x3 to find the points. However, if origin include in the plane ABC, then A1 B1 C1 A2 B2 C2 A3 B3 C3 is not invertible. Then we actually solve lambda naught 0 a lambda 1 0 b lambda 2 0 c is equal to 0 x, where 0 is any o is any point not in the plane ABC. In alternative, to use certain will choose cross product. But so in such a situations, we then use cross product of vectors to compute the situations. Thank you.